So I've gotten really into collecting things recently.
Oh yeah? What have you been collecting?
I've been collecting, like, Lego, and I've been collecting, like, board games.
Oh yeah?
Yeah.
I've been collecting too.
Oh yeah? What have you been doing?
I've been 4.4 collecting like radicals.
Neat.
Speaking of like radicals, let's kick things off first by talking about like terms. Now, we've got just a list of terms below. What I want you to do before I even start with anything, just go ahead and tell me which ones are like. Well, you don't have to say it out loud. I can't hear you.
Huh.
But just on your sheet of paper, write the ones that you think are like terms next to each other. And if that wasn't enough time, I hope you paused, because we are back and we're going to be talking about like terms. Now, when I'm looking at this one, I'm going to look at my 2x squared first. So 2x squared, what is that like? Well, it's not like 4y cubed or just x, but it's also like negative 5x squared. Anything else? Not 47, not 2x, not xy cubed, not 1. What about my 4y cubed? Well, that's similar to my 8y cubed. And what, oh, I should have highlighted that or underlined it. Boom, there, okay. What about my x? Well, that's similar to my 2x. And what about my 47? Well, that's similar to my 1. Now, you probably did all of these because you're just totally smart. But what makes these terms like terms? Well, if we're just examining the pairs that we figured out below, we can say they all have the same variable, right? These guys both have x's, and these guys both have y's, and these guys both have none. But that's not enough, because if it was just variables being similar, then why aren't these guys like terms? Well, they all have the same variable and the same exponents on that variable. Same exponent on that variable. Oofed. So that's what makes the that's what makes the terms above like terms, right? These both have x squareds, and these both have y cubes, and these just have x's, or x to the power of 1s. And these technically have any variable to the power of 0. But they all have the same variable or lack thereof, as well as the same exponent on those variables. Notice that when we were looking at our like terms, it really doesn't matter what these coefficients are. Look, 2 and negative 5, what's similar about them? 4 and 8, 1 and 2, 47 and 1. It doesn't really matter what the number value is. It was just the variable and its exponent. In the same way that we can collect or identify like terms for polynomial expressions, we can simplify radical expressions by also looking for like terms. Now, just like we did above, we're going to ignore the coefficient completely. Doesn't matter what's in front. What really matters, or what mattered above, was the exponent and the variable and the exponent on that variable. When we're talking about radicals, all we really care about is the radicand and the index being the same. So remember, if we're looking at my radical, my radicand is the number inside here. I don't know, maybe like 3. And my index is the number that's here, or the lack of number that's there. So, for example, if I wanted to find a like term to 2 root 5, I have to find something else that has a square root of 5 attached to it. I can't have something with a cube root of 5 because then the index wouldn't be the same. So square root of 5. Oh, there's 2 of them now. Oh, I should probably write that in pink. 2 root 5 and negative 5 root 5. I want you to take a pause and try to identify the rest of the like terms in the collection there. And whoop, maybe you're back. Welcome. I'm so glad to have you. Taking a look at the next one, 4 cube root 5. So I'm going to look for another cube root 5, and here we have it. So 4 cubed root 5 is like to 8 cubed root of 5. And 4, well, 40, no, and 10. There we go. 4 and 10 are similar because they both have a lack of a radical. And then 47 root 2 and just root 2. 47 root 2 and root 2. So we are able to look at our like terms with radicals as well. So looking at those like radicals.
In simplifying these, as Tib said, it's just like playing with polynomials. So if I had 2 root 3 plus 5 root 3, and I'm like, how do I do this? Why did you scream like that, Tibbs? That wasn't me that screamed like that. I could pretend it's just like 2x plus 5x. It's just that the x's are root 3's instead. And this one I would say is 7x. How many x's do I have? Well, I've got 2 here and I've got 5 there. I've got a total of 7 x's. And don't call any of them. Here I have 2 root 3's and I have another 5 root 3's. How many root 3's do I have? Well, I've got 7 root 3's. So our coefficients are just helping us count how many of that term we've got. Oh, purple and green. I'm like, joker. I'll take this. So that's 7 root 3. Let me look at this. Next one, I'm looking for terms that are like root 2. And I think, oh, this is close, but ooh, that index is different. So I don't actually have any like terms here. Which is sad. So it cannot be simplified. I dare you to try the others before we show you how it's done. Oh, we're going to show you how it's done.
Wonderful. So now that you're just verifying your answers with what we're showing you, we're looking to collect our like terms. So if I'm looking at my first term here, I have 4 root 7. So I'm going to look for something else with a root 7. And here we have it, folks. We have another 2 root 7 just hanging out. So we have a total of 6 root 7s. Well, what I notice is I also have some root 3's going around. And I have negative 3 root 3 and positive 2 root 3. And when I combine them, I get negative 1 root 3. But what I noticed from before, like if I was doing negative 3x plus 2x, I wouldn't leave my answer as negative 1x because I would get an E1 error, not fully simplified.
Yeah.
I would have to write negative x. That applies in the same way to radicals because it's saying like negative 1 times root 3. So to fully simplify it, I would just say minus root 3. I wouldn't include that coefficient of 1. All right. Last but not least here, we've got some cubed roots of 6's, and I'm going to collect those. So 5 and negative 3 will give me 2 times the cube root of 6. And then I have just the square root of 6. And 2 plus 1 root 6 would give me 3 root 6. For whatever reason, I noticed that some people find that when there's not a 1 written there or a coefficient there, for whatever reason, they sometimes think it's 0. Please be cautious. Just like how we wouldn't write the 1 here, it's still implied, it still exists. It's just not implicitly written, or explicitly written. It's implicit, yeah. So please be careful. And again, this is cube root, this is square root, so we cannot combine them further.
In our next examples, we have some terms that don't appear to be like radicals. Right? Look at root 24 and root 6. They've got different radicands. And like, well, those can't be combined at all. What we'll want to do is make sure that each radical is in fully simplified form, fully reduced, that is. And then once they're both fully reduced, or once they're all fully reduced, we can move on and check if anything else could be simplified. Like looking at root 24, we can say that that's equal to the square root of, I need more space here, 4 times 6. And we're going to use our reducing abilities. Now, as we do that, we do need to make sure this root 6 at the end here is still accounted for, and it's still part of our expression. So we're not just reducing this separately on its own path and then throwing in this negative root 6 at the end on the very last line. No, it's got to be part of this expression the whole way through. We're keeping that expression intact. Woolly? So in simplifying this, we've got root 4 times root 6, which is 2 times root 6, and we're still subtracting this root 6 at the end. So this part is still there, this part is right here. And then for our final step, we have 2 root 6's, and we're going to subtract one of those root 6's, leaving us with just 1 root 6.
Ooh.
Yeah, it's not bad. I'm going to do one more over here. Root 50 plus root 18, those don't appear like at all, but I have mathematical skills. So I'm going to write root 50 as the root of 25 times 2, because 25 is a perfect square. I'm going to write root 18 as the root of 9 times 2, because 9 is a perfect square. I know 2 is not a perfect square, but that doesn't matter to me. So this root 50 became this root 18 became this. And root of 25 times root of 2 is 5 root 2. Root of 9 times root 2 is 3 root 2. Ooh. And now I can see that these are actually like terms after all. We have 5 root 2's and we've got another 3 root 2's. In total, how many root 2's do I have? I've got 8. I have 8 root 2's.
All right. So taking a look at these next examples, I want you to try them on your own. Give them a pause. Well, give this video a pause and then give the examples a go. And then come back when you think you've got it. All right, you're back. Oh my gosh, you're so quick. All right, so we're going to take a look at these. And just like what Mr. A said, we are going to try and simplify them to be mixed radicals first, and then see if we have possible like terms to then collect. It is possible that there might not be any like terms to collect, and that's okay too, but we won't know until we simplify. So that's always going to be your first step. So root 20, I'm looking for factors of root 20 that are at least a perfect square because we're dealing with square roots here. So I have 4 and 5. And then notice when we have this negative 3 root 45, you might be thinking, what do I do? It's already mixed. How do I simplify it further? But don't let the negative 3 fool you. It's just multiplied by our root 45. So I'm going to treat the root 45 like I would any other entire radical I'm converting to mixed. So I have 9 times 5 here. And as I go ahead and do that, ooh, you know what? Mr. A did this, and I kind of liked it.
I liked it too.
Anyways, okay, beauty. Here we are. So, our root 20, which is our root 4 times 5, turns to 2 times root 5. And our negative 3 times root 9 times 5, well, that will give us negative 3 times 3 root 5. And we can, ooh, again with the color coding, yes. We can further simplify this second term here because negative 3 times 3 will just give us negative 9 root 5. And look-de-doo, we've got lots of root 5's up in here. So as we collect them, we should get negative 7 root 5 as our final answer. Locking it in. All right. Last but not least, take some time and go ahead and simplify these on your own. And we're back. Okay. So negative. Again, we're dealing with square roots, so I'm looking for a factor of 27 that is a perfect square. So I have 9 times 3. Now I'm looking for factors of 5. Well, 5 doesn't actually have any perfect squared factors, so I'm just leaving that one as is. 80. Remember in one of our first Second lesson, I think. We're like, oh, 80, well, that's just 4 times 20. But then Mr. A's like, oh, but there's a faster way. And it was root 16 times root 5. I remember that too. So I'm just going to jump there. And then I have 2, and then root 12. Well, root 12 I could write as root 4 times root 3. Also, if we're just kind of jotting our memories here, remember way back when we were talking about radicals? Oh, we were so young. We said that the radical sign had to encase the whole entire radicand. This is where I find people don't necessarily complete the whole radical sign to cover everything. Especially when you have that like multiplication going on inside. Please, please, please be careful that your radical sign totally covers your radicand, because otherwise that could lead you to the road of communication errors. I know, scary. All right, going here, I'm just going to simplify these. So I'll have negative 3 root 3. This 3 root 5 stays same. I have negative 4 root 5. And then I have negative 2, and then times 2 root 3. And I'm going to write that exact same thing down. Except this time I'm going to write 4. Now, you do not have to do these as separate steps, but if that's something you prefer, then great. But it's completely up to you. And then looking for like terms here, I noticed that I have a couple of root 3s that I can collect. So negative 3 and negative 4 give me negative 7 root 3. And then I have a couple of root 5s going on here. So 3 plus negative 4 will give me negative 1 root 5. But again, I don't write that negative 1. I just write negative. And there we have it. So we'll have negative 7 root 3 minus root 5.
There is some practice. Woo! Let's go!
And in fact, there's also some answers down there if you want to check your final answers there to make sure they are same. Woo. But otherwise, that is it. That is all for today's lesson.
Nice.
And we'll see you soon.
Bye.
Hasta la pasta!
Wait, what?
Hold on, what was it, the thing?
Hasta la vista?
No, but it was funnier.
Adios, muchachos? That's what you always used to say.
I don't know. I saw it once on TV and I laughed, and now it's just...
Hasta la pasta.
Hasta la pasta,
It's
baby.
funny.